operation. And so it's something that you need to define. So I think it would be nice to have a group of people to discuss how to set these systems on. Another point that I saw, let me say that is more science discussions, that's open question. It's one very important question is the ice mass diameter relationship. That is very important to the model. It's the model, all model parameterization of microphysics depend from this relation. Actually, is it's respond to the density of the ice. So it's something that it's completely unknown. Another unknown information is the layer of the mix phase and how to have the mix layer between ice and water that is can completely bias any radar polarization radar utilization, because all the software and make classification consider that above 0 degrees completely ice. So if you have water, you have different response. So this is also some important topic of research that is we don't have questions, we don't have an answer for that. So I see. Let's see what and. I see these two important topics of research in the process. Of course, the satellite precipitation guides has another relate to that, and about the radar too. So I pass the hand to Luca to talk about the radar calibrations.
I would like to introduce the radar calibration from a more general point of view. Now, after several tubular experiments, I think people have learned several things about what instruments can provide and what they cannot provide. Basically, all the experiments in tuba, like many other experiments all over the world, are based on some sites where you have ground instrumentation, like dynamometer, rain gauges, that provide some important information about the DSD, what is at ground. Then you have some profilers. Up to now, only mainly the MRR, a micro ring radar, has been used. Is something that can provide you information to extend what you have at ground to the entire column. And also you have you have one X-band dual polarization radar. It's placed not too far from this place where these places where most ground instrumentations are, because you want to have enough vertical resolution. For this reason, you do RHI. You don't want to be too far from instruments, because you want to have a less influence of attenuation. So you have several instruments that look at the same phenomenon. They have different results. They provide different results because they are different from the point of view of measuring approach. But also they have some difference in calibration. For example, if we look at ground sensor like different dynamometers, we rely mostly on manufacturer calibrations. We can do some experiment with metallic sphere, but that's all. But if you have shown that a Josval-Vogel disdrometer and a Parseval co-located very nearby, they give different results. This is because they are based on different principles. With the radar is of course it's a very important calibration is a very important topic, because if of course, if you have a dual polarization radar and you want to measure liquid water content or rain, you can rely on the differential phase shift, which is not affected by absolute calibration, but most of the information from historical reason, and also because differential phase shift is not so a very measurement on refinement. So if I am a radar data provider, I want that I would like that my user would trust on my data. Actually, calibration of radar is not an easy task. Within the GPM community, we are trying to develop some standard calibration procedure. We divided the process in two phases. The calibration, the calibration is based on standard targets. One target could be the sun. Other target could be a metallic sphere. It could be maybe in the next campaign we could perform a calibration with a suspended sphere, because a sphere is a target of a known radar cross section. It's something that I cannot do in Rome, because there are a lot of roads close to the radar. Maybe if there are no environmental limitations, something that can be done. I think if you are hosting some ARM radars, I know that they are trying to develop a calibration based on dihedral. So I think for the next campaign, a specific calibration experiment should be planned, and then in addition to this, we can perform all the other techniques that can we regard them as a verification of calibration. For example, comparison with satellite that was shown by Carlos this morning, or a comparison with ground instrument properly located, and also self-consistency of measurements in rain. But I think we should perform a calibration experiment next time to be sure what about the quality of data that we are providing. In the case of X-band radar that are moved from one part to another part of Brazil, I agree with Carlos. There is a problem of aging. For example, something that is known that is aging is the radome. Hydrophobic properties of radome are changing in time, so you never know the attenuation that is induced by the radome wetting. So something that we have to consider carefully. Okay.
I have two questions. One addressed to you, and other to Carlos. So it's when you do cross calibration, it's a different geometry, a lot of approximations. And when I see that 2D BZ, it's different. I don't know. This is not the arrows. I don't know. My feeling is that excellent if you have 2D BZ, because it's different geometry of co-localizations, parallax. So I don't know what you consider, and to Lucas, my question is, you were suggested to do a sphere calibration for the X-band, S-band in Manaus.
Using a sphere calibration, some solar scan.
Solar scan, it's a routine standard.
Yes. So just
and cross calibration with the S-band, because it will be collocated.
Cross calibration with the S-band means that you are sure that S-band is properly calibrated. The comparison with the satellite is an advantage, because satellites, the sensor is always the same, so it's if you can compare different radar against the same sensor, which is a twin PR or something else. If you compare an S-band radar from National Weather Service with an experiment with a research radar like the Gematronic Explore radar, you never know which one of them is correctly calibrated. Carlos.
Yeah. But the question is, we have done in the right direction for Fortaleza and in the wrong direction in Belém. Why? What do you believe that is the radar that has changed the calibration or the weather system?
Remember that the radar arrived in Belém was completely. The engine was kind of apart.
Yeah, that was very difficult because we bought. Yeah. Yeah, no, but I think it's interesting just to the people understand the difficulty. From Fortaleza to Belém, we contract transportation. That's a very nice truck. Last year, climatization, everything, it's nice. When the radar was delivered in Belém, and we sent the engineer, he take picture, was the oldest truck I have already seen. I don't know how the truck has been changed during the way, but arrived another truck, very old, and I didn't understand what happened, but this is something that happened.
So you're using that as a reference One of the things you can remember, so you're having every day you do the calculation, every day, let's make sure that the power was being perfect. When you find out you're fighting the out. Okay. So it's very important to look for that.
Yeah, but Luca suggests a sphere calibration. We have done it in, unfortunately, or is not here, we have done with the MIT radar in Africa. And this was very difficult and, and a little bit imprecise. I don't know if you have done not the right procedure, but it was very difficult. No, you have clutter, you have a lot of problems. So I have noted here that it's recommend radar sphere calibration for Manaus to define a working group of radar to set up the field campaign in Manaus, because you have CIPAN has 10 S-band radars, and we need to discuss how to intercalibrate all these radars and have a very good strategy. And also, I think it's very important to have in Manaus a completely open field for the X-band radar, no clutter. And so we need to. I'm discussing with CIPAN to try to put the radar on the roof of the CIPAN. That's very high. I think the highest on the region, and that's very flat region, but the trees are very high. So if you don't have a building, you need to have a very high tower. So it's something that. So as a recommendation, I note these 2 points.
In addition, to find a way. In addition, is to find a way to monitor the transmitted power. Maybe at least looking at some LED. So. Sorry? Yeah. Concerning intercalibration, so when you perform a calibration, you would like to be sure that your radar is calibrated within 1 dB of accuracy. Then you can check, it is something that you can obtain using a set of technique like a sphere, some calibration, standard reflectors, and so on. Then using comparison intercalibration or calibration with the satellite or whatever, likely you have maybe the same bias of calibration, but the spread of the bias estimate is quite large. So, for example, if you say that the mean calibration bias, according to your experiments, is 3 dBs, but the variance of the mean of calibration mean is 10 dB, maybe you cannot be so sure about the calibration. So this is why we distinguish between calibration and verification of calibration. Calibration is an experiment that you can do, and then you can set up different techniques to monitor in real time calibration by comparison with other sensors or verifying the properties of your measurements.
Okay, so let's move to satellite.
Yes, one important thing about, I believe, that Shub experiment, it's part of GPM, ground validation. So we need to work with satellites. So as was pointed out by Nicholas, some tasks are very hard for satellites, and something can be done with satellites. So I believe, we need to move to make this kind of microphysical values validation stuff, like Audrey showed this morning, to look at the microphysical, what happened in the microphysical space to improve the algorithm. Another important thing is to look at what happened with different satellites, because we have right now several imagers like SSMIS or TMI, but we also have a lot of cross-scan sensors that are not designed for retrieving rainfall. They are designed for other stuff, not for retrieving rainfall, but they are very useful for our community in terms of satellite rainfall retrieval community. So we need to deal with that. We need to work with that. Well, some of preliminary stuff was done by Ramon, looking at what happened with AMSU data, see if he can improve the method for retrieving rainfall using that satellite, because we have NPP, we will have GPSS in the future, and METOP, of course, so we will have more information from those satellites, and we need to work with that. There's no other options if we want to get a good temporal and spatial coverage. So this is my message from the satellite rainfall retrieval community.
I would only agree with what was said already. I think it's very important to have well-calibrated radars, or even if you don't have very well-calibrated radar, I think it would be important that the rain products that are provided with validation in mind are provided with some sort of error bars on the rain estimate, because any validation, any comparison between two instruments or two products should require that you have error bars on both products. And that's something that is really important. And it's not easy. Okay, it's not easy, but I think any estimate should come up with an error bar. Either you consider that your estimate is a reference, like it's a rain gauge or a radar, but you should come with an error bar. So that's really the product validation aspect. And also, as I said, I think in the near future, most of the satellite product will not provide you with only one rain rate, but probably with a distribution of rain rate or with a probability of rain intensity, pretty much the same way models provide ensemble forecasts. And this also probably needs to be, we need to think about or to think how to design validation techniques that would kind of function in a probabilistic space or environment. So instead of comparing 23 millimeter per hour and 27 millimeter per hour, how to compare distributions, how to characterize two distributions, and so on and so forth. So I think it's really something that we should keep in mind for the near future.
Yes, and also I believe that we need to move forward to some kind of object-oriented validation techniques, because sometimes the validation or the traditional validation technique like POD, FRA doesn't work very well, because you have a feature but it's slightly displaced. You have a displacement between the ground truths and what you're trying to validate, and your statistical values will be very bad, but perhaps it's because it's displaced. So we need to move to this kind of validation stuff oriented to objects instead of traditional.
This is particularly critical for satellite validation. Once again, satellites are not designed to retrieve rain in the courtyard of your summer house. For that, you can have 3 rain gauges or a radar that'll do a much better job. Satellites are designed to retrieve rain over the whole globe or over large regions. They should do a good job on a smaller scale, but that's not their initial design, and that's something you need to keep in mind when you use any satellite product. Satellites were designed to retrieve rain over Africa, over Brazil as a whole, not necessarily over really small places. So you can have some serious shift of spatial shift. For instance, Audrey showed the image this morning. You have the rain right over the radar, but the brightness temperature shows that the convective core is shifted by about 5 or 10 kilometers to the northeast, and there's no way your retrieval algorithm can cope with that. The retrieval algorithm will put the rain shifted by 10 kilometers to the northeast. That doesn't mean the estimate is bad, that doesn't mean the product is bad, it means it's just what you have in the measurements anyway. So that's very important.
I would like to add something about the role of radar in validation of satellites. We have seen 2 roles in this presentation. One is the ability of the dual polarization radar to provide information about microphysics, that is an input for a retrieval. And the second one is the comparison of rainfall field at ground. In both cases, I would like you to pay the attention on the fact that sometimes we interpret radar measurements like instantaneous measurements. When we deal with microphysics, with vertical structure, sometimes we have instantaneous measurements based on RHI, and sometimes we need to perform several PPI sweep to have a volume. Also, so a volume is not an instantaneous measurement. Also, there is a role played by the distance from the radar, because as far you go from the radar site, your resolution could be not enough to provide you good microphysical information. And this is also true also for a statistical validation, so rainfall at ground. For example, if you Nicolas showed some comparison with the scale of X-band radar. So I don't remember how many kilometers are taken from the radar, these measurements. But for example, if you rely on long distance radar like S-band radar, and you try to compare satellite pixel with that is 300 kilometers far from the radar. So the satellite is not measuring rainfall by definition, but the radar is measuring something that is happening 6 or 7 kilometers above the ground. So it's for both for physical and statistical validation, it's better to rely on a small size. So it's good to have such a validation site with that can provide high resolution measurements, both in terms of vertical resolution and spatial resolution.
Yeah. One point that I think it's important, and it's in the goals, one of the main goals of Sugar project is the warm rainfall. And I think I would like to put on the table this, is there any possibility or it's impossible to retrieve rainfall? So Alain is trying to do that. He have just made several simulations. I don't know if you want to say something about that. Are you happy or not?
Well, as I was saying earlier, I think the warm rain using passive microwave is going to be very difficult. Or we need to really find an original idea to solve.
That's the good instrumentation. You have everything. You don't care about you are in the ocean or land or you are it's warm cloudy or not. You can get the precipitation. And to cover the temporal resolution, you have a lot of passive microwave radiometer. So, but I found out that the cost of a passive microwave radiometer is the same as the cost of the radar. So I'm really, I always thought that the radar was much more expensive. This is why. But actually, it's more industry, countries problems than scientific problem. So in my mind now, I'm much more motivated to have an active radar with the Japanese at the same cost as passive. And so to have the PPA, and I'm much more motivated to have a radar, and if the people also are motivated, need to help, we need to have to pressure Brazil Space Agency to help to go further.
I have a question. We have several data sets from several Shuva campaigns with ground measurements, profilers, and radar, and so on. I have seen presentation using or a radar or dysdrometer, but I have seen only one presentation who tried the radar.
So just one comment before Alan start, because Alan, you're gonna present. I think your presentation can answer this question because you're really gonna show that.
Yeah,
right?
some of them.
So my suggestion, as we have time that is going, that Alan come here, answer the Lucas question, and start his 5 minutes presentation. So after the 5 minutes presentation, I have 5 minutes Sapus presentation and 5 minutes Thiago presentation. 2 minutes. Good. So you have 7.
Okay. Não, eu tô indo.
So, when I was using all this data, I have some problems. Many with the radars. For example, the micro-rain radar. When I was looking for the liquid water content in a convective system, okay, I know there is a lot of papers about that. Peters 2005, Peters 2010. It's the guy. Yeah. A primeira 3. Ou não, o depois.
So some of part of my research, I didn't use the microwave rate anymore because of the attenuation, of course. But if you're looking for something in starting point log, okay, it's very good. There is a lot of agreement between the expo and the microwave rate. So I start with the microwave ground-based radar meter. It's the MP1000A. It's from the radar metrics. So I have a lot of problems with that also. So I have some issues about this data. I will try to do this faster than the last time. Okay, this the data set. What you have? This Alcantara, everything's processed. Okay, it's okay. Fortaleza, we have to reprocess the data because we have some problems in the pressure sensor. It's all the retrieval was wrong. So, but the raw data was very nice. The Belém, it's okay. The process. The one problem in Belém is because the calibration wasn't in the same site. I don't know what's happened, so I wasn't there. In fact, the Paraíba, we have a very nice calibration. The data is processed. We have some problem with the retrieval because I don't know why, but I sent the data for the radiometrics and they have processed everything. In Santa Maria, we are using a new neural network system. It's not the neural network, but the system to retrieval. So it's not so in the zenith, but in the other angles. So it's I needed to check all the readmes and make some programs to see what's happening in Santa Maria. To download the data, it's very easy. Right now, you just need a login and choose the experiment, type of instrument. In this case, radar meter. The instrument in MP1000. It's just, and in this case, in Alcantara, we also have the Admirari. It's the only side when we have the both. The type of data is experimental. You can choose the level, the site. It's just one site for each experiment. The data you want, okay, and the download. It's easy. This the data extruder. When you have finding data, you can open Microsoft Excel. It's very easy. So you just have the time and all the channels and the measurements and surface sensors. It's very, very friendly. The level 2 is also friendly. The same instructor, but the relative is different. You have the profiles. It's the same profile for each campaign. And the zenetic measurements in Santa Maria, we have more information about that because we have more angles to retrieve. So some issues you have taken account when they are using the radiometer, for example. Many papers has the problem with the rain effect. So the bite temperature, the temperature it's just one for the raindrop. In the most of the cases, it's the película in the radon. It's the film. It's not the atmosphere. It's just the water of the radon. Okay. Radon it's a protection. Is okay. And okay, if you look for the charts, it's the bite temperature versus the rain rate. You have. Okay. It's the all difference when you have the rain. The same thing for no precipitation and rain clouds. It's very different. So when you have rain, it's happen with the brightness temperature. Oh, again. Okay, let's head on. I use geography time, and it's very nice. Okay, this is saturation here. We have wet Hadomi here. I suppose it's not a good data. You don't have to use it. It depends what you want. For example, if I retrieve the liquid water in the surface, the rainway in the surface, it's very nice. There is a lot of paper for this retrieval system, but for cloud in the rain, it's not so good. Liquid water in the no rain system. This is a fact of the different neural networks. It's just a test. I use all our neural network to see what's happened, what's the difference, and it's very dependent. You have to choose the right neural network, because they don't, the result was not very good. This result from Sapusi. Sapusi found these errors in Alcantara. It's just happened there. It's only happened in Alcantara. It's a new outline in the MEP. When you have close to the midnight, close to the noon, close to the noon, we have this outline. This is a problem with the radiation. If the retrieval is not so good. This is an example of the profiling noon. So we have to take it off. This is calibration. It's just using for Fortaleza, for example. Okay, the calibration is very well. The bottom temperature is the maximum 1 Kelvin. But if you are looking for something using the radiometer to do simulations, we have a very light bias. So my question is, okay, if the calibration is okay, why the simulation is not? The problem, I guess, it's absorption of the continuous water vapor, for example. Because when I was in Fortaleza, we have a very dry day when the campaign. And I compare 3 or 3 simulations. The result of with the observation was very nice. But in the other days, it's not worked very well. So we have to discuss that. The expo and the microwave. So when you have a convective system, like I have shown in the last presentation, so a lot of attenuation. So all the column is not safe for the microwave. It depends on the precipitation of kind of system. This it's a vapor. For example, it's rain in the cloud, but not in the space. Okay. If you look to the data, the retrieval of liquid water content from the ground-based radiometer, it's just an effect of the raindrop. It's not the cloud rain. Okay, so you have to take into account. But if you have a stratified system, we have a lot of agreement. We have agreement between the radars. It's very good. There is no problem. The liquid water content is closer between them. Okay. I think it's the last one. So, any question?
Thank you, Alan. So this is some issues about the MP3000 and MRR. So the data, it's already processed. You try to do calibration in all the operations. So the data, it's available on the data bank. And if you have any question, can address to Alan. Yeah, but anyway, it's the top. So we use the data down there. So now, suppose you just present the status of the GPS data.
Okay, I will be very fast. This presentation, I'd like to present the data processed and available in website in Chuva about the IWV observation from GNSS. This next slide, I will present with campaign in Precipitation and the others slides the same format in this special distribution of the station or GNSS receivers. In this some figures about the antenna and receivers used in which campaign. Alcantara in Precipitation experiment, 2 receivers in dual frequency was used. Sample rate 1 second, elevation mask in 10 degree, 30 days of continuous data collection in the first experiment. Sorry. In the second experiment, 2 receivers was used in Fortaleza, and the similar configuration of the collect of the data, and the third experiment is the experiment with Dataset and network used in Chuva, where 50 receivers of dual frequency were used, and this distribution of the data and the receivers in this campaign. And the Chuva Valley, 6 receivers and dual frequency were used, and sample rate the same, 1 second, 10 degree and the elevation masking, and this campaign is a longest experiment, and about the 4th month of the continuous data collections. And the last campaign, Chuva Sul, 25 days of continuous data collection, and 4 receivers were used. This slide shows that the flux chart of the generation of IWV, it is possible to see the 3 levels of data. In the first is the binary file from GNSS receivers, and the second is some after the next processing. The first processing using Gypsy Oasis 2 is the software from JPL and from NASA that uses some files converted using other softwares, scientific softwares that do some quality control in the data and convert in the international forensics, international format in the forensics. In the last level is IWV that you converted is ZTD and meteorological data. In this file is interesting because there are some meteorological data, temperature, humidity, and temperature, pressure, temperature, humidity, and 1 second in the sample rate. In the last slide, present the structure that used in the website, server Pacaraca and CPTEC IMP RB, and this experiment, the kind of data, the level of the data, and this structure is the same in the other data, and the data final IWV are presented in this file, this kind of file in this format, and the time and Juliet second of the year and the values. And there are some README available to some special information about what station and date. And probably in the future, new version of this processing using other software is probably better sample ratio or corrections. Okay,
So the chat will just talk about the radars and if there is some additional information. Oops. But yeah.
I will be quickly as possible. So in terms of radar data, what we have, the X-band, Gematronic X-band that was discussed here extensively, and several S-band radars that it's not our responsibility to check calibration and everything. This is Air Force radars. We don't have that much authority over them. So for the X-band radar, all the data, all the raw data is in ASCII format and universal format for the level, for the volume scans and the RHIs. And we have copy for the S-band and the X-band radars. It's a binary format. You can read with grads or any write your own code. So very simple. All the data has the README and some codes to read all this data. In terms of levels, the level 1 is the data with the correction for attenuation from the Z-Fi method. And as Luis told yesterday, we have for some experiments the coefficients for the wet radon correction and the ZDR. Sorry. In terms of data availability, the Alcantara, the X-band radar in Alcantara is not the Gematronic X-band radar. The radar, the X-band ran relatively okay in Vale do Paraíba. We have some gaps here. In Belém, Fortaleza, it was just 1 or 2 days that we had some problem. The radar didn't work in Santa Maria. In terms of S-band radars, we have 1 in Belém from CIPAN. This data is in universal format. We have 3 radars in Vale do Paraíba. 2 is in HDF5 format, 1 in universal format, and 2 HDF5 formats in Santa Maria. We have 2 Doppler radars here, and and 1 here. Yeah, I already said that, but just as a comment, we have some, Morales found some problem in the level 1 and level 0, the universal format for the RHIs. So I will replace them next week. There were some errors in the codification. And we have a copy from 2 to 14 kilometers for each 500 meters for the X-band. And we have copy from 2 to 16 kilometers, each 1 kilometer for the S-band radar. I guess that's it about the radar. All this, the ASCII files have some codes to read them. There was some errors, but Henrique correct some of the codes, and it's there available for everybody. Any questions? Any comments?
So thank you, Thiago, and we need to close the section now. We have the coffee break outside. I invite